Sir, I'm getting some error where I'm launching the structure file, sir.
Okay. So the TB underscore gate structure. Okay,
Yes,
that
sir.
file.
Yes, sir.
Okay. ठीक है, I'll just check it. Okay, so TV underscore and dot P. You haven't changed the input and you have open. We have changed that to the XYZ, na, Mohammed?
Yes, sir. I've tried with XYZ also. It is giving the same error, sir. A reg is not a legal value. It is showing, sir.
Okay. अभी
Yes, sir.
अभी इसमें क्या किया है मे बी दैट में वो कॉन्फ्लिक्ट क्या हो जाता है अभी ये जो एंड गेट है ना इसमें हमने
Sir.
वेरिएबल्स यूज किए सी ए और बी ओके
Right,
और
sir.
ये
Okay.
इस एंड गेट का डेफिनेशन है वेरिलॉग में अवेलेबल और इस पर्टिकुलर स्ट्रक्चर के लिए क्या हो रहा है, हम उसका टेस्ट बेंच लिख रहे हैं यहाँ पे, राइट। तो यहाँ पे एंड गेट अंडरस्कोर स्ट्रक्ट ही हम इंस्टेंशिएट कर रहे हैं, ओके। तो उसको ऐसे लग रहा है वो जो क्वांटिटी है जिसका मतलब ये हमने स्ट्रक्चरल वे से एंड गेट इंप्लीमेंट किया है, बट अब जब हम उसकी कॉपी ले रहे हैं ना यहाँ पे, तो उसको ये सिग्नल्स ओवरलैप हो रहे हैं, मतलब सी ए बी, एंड उसका नेमिंग कन्वेंशन
अच्छा
ये जो है ना, विद द
हाँ
नेमिंग
सर।
कन्वेंशन उसका मैपिंग है। दूसरा एक होता है वो पोजिशनल कन्वेंशन होता है, मतलब वहां यहाँ पे जैसे पोजीशन डाले ना, सिमिलर
हाँ सर।
पोजीशन आप यहाँ पे भी डाल दो वैसा। तो वो
अच्छा।
पोजिशनल कन्वेंशन नहीं ले रहा था, तो उसको नेमिंग
हाँ।
कन्वेंशन कर दिए, ओके।
ओके सर।
मतलब अभी
हाँ।
इसको तुम अगर इसके बाद भी लिखोगे, ऐसा भी लिखोगे, तो भी वो सही में आएगा।
अच्छा सर, ये हम जो साइलिंग्स में एरो लिख के करते थे वैसे ही है ना सर ये?
राइलिंग्स में क्या लिखते थे?
एरो लिखते सर, पोर्ट मैप करके।
हाँ हाँ हाँ, वैसे ही है वो, वैसे ही हो।
हाँ हाँ।
VHDL में वैसे लिखते थे, हाँ ऐसे
हाँ
ही
सर।
है वो।
ओके।
ठीक है,
हाँ सर।
तो फिर इसका सर ले लो आप, दिखाएगा एक बार देख। हाँ ठीक है। So after this, uh, we will see half adder implementation. So Mohammed, can you implement the half adder using data flow modeling style using logical expression, or should I explain it again?
No sir, using logical expressions I can implement sir.
Okay. So after that implementation, I will show you how to use two half adder to create one full adder
Yes sir, yes sir.
using structural. Okay. So you
Okay,
just
okay,
create a half adder.
okay sir, okay. हेलो सर.
हाँ मोहम्मद, हो गया?
Yes sir, I've got the
Have you
output
checked
also.
functionality?
Yes sir, yes sir.
हाँ हाँ, good.
So
So
I
I
will
will
show you now how to create a full adder.
Okay sir.
Okay, Mohammed, I'm just checking my system. Okay, just wait.
Yes sir.
Okay, so my half adder code is in this file ha.v. Now I need to create a full adder. So this ha.v is in the same folder. So in Chetan underscore Verilog1. So in that folder only I am creating that full adder file so that I can instantiate this half adder to construct the full adder. So if you see the diagram of a full adder using a half adder, so here you can see. So is it visible to you properly, Mohammed? Am I audible to you?
Yes, sir. Yes, sir. You're audible and it is visible, sir.
Yes, I think. Okay, his voice is not audible. Okay. So, Mohammed, are you there?
Hello.
His voice.
अपने हेडफोन निकाल के रखा है
Okay. Hello. आ रहा है क्या आवाज?
Hello, sir. Am I audible, sir?
Yes, you are audible. Am I audible to you? Yes.
Yes, sir. Yes, sir.
ठीक है. So now I have created a half adder file here, half adder.v. So in that I have defined the half adder. Now I want to use that half adder to construct the full adder. So I need to follow the structural modeling style for that. So here you can see there are two half adders and one OR gate to implement the full adder. Okay. So, and if you talk about this entire full adder module, so this will be like, so this will be like this, right? So this will be the full adder module. Okay. Now here, these are the inputs P, Q and carry in. And sum and carry out are the outputs. Okay. So while defining that module, in the input list, I will mention these three inputs. And in the output list, I will mention these two outputs. Okay. And if you see here, for connection of this half adder and OR gate, we will require some internal wires. Okay. So this will be like S1 wire, this will be S2, and this will be S3. So in the structural, what we need to do, we need to instantiate two half adders, okay, and we need to instantiate OR gate, and we just need to make the connection like what is shown here, okay. So if I talk about, if I instantiate half adder, if I say this is a half adder U1 and this is a half adder U2, so how I will do that? For example, I have mentioned half adder module name as a HA. So I will first say HA, that is half adder, then instance name U1. Okay. Now in the half adder connection, for example, in the half adder, if you see, first I have mentioned two inputs, then sum is there, and then carry is there. So in the similar fashion here, I need to mention that. So first two inputs are what? First one is a carry in, that is external input, and then S1 is there, S1 wire. So these two are the inputs. So I will mention here carry underscore in. Okay. So carry in. The next input is S1. Okay. And here they have given sum and then carry. So first sum is sum variable that is connected to, and carry is S3, right? So this is the first half adder. And if I talk about the second half adder, so that will be having two inputs, P and Q, and output S1 and S2. First sum, then carry. Okay. S1 and S2. Okay, so two half adders are there. Now if we talk about OR gate is also there. So OR gate instance that is already available in Verilog. You don't need to define it. That definition is available in Verilog, right? So I am using OR gate instance. I am saying U3. Okay. Inputs are So in the inbuilt primitive of Verilog OR gate, first we need to define the output. So what is the output of OR gate? Carry out. Okay. So I just underscore it. Carry out, and inputs are S3 and S2. Okay. So these three are the important statement here. Okay. So have you understood this?
Yes, sir.
Okay, so I will just write a code in the similar fashion there. You can also write with me so
Okay.
that module ladder, there are inputs like a P, Q, carry in, sum, and carry out are the output. Here I will put S instead of sum, so variables will not get overlap. Okay, and while choosing the variable for this full adder, Mohammed, you just choose the different variable names. Okay, input names.
Okay.
So whatever you have used in the half adder, don't use in full adder.
Okay.
So I will require 3 internal wires. That's why I am taking wire S1, S2, and S3. So like this way. S1, S2, and S3.
Yes, sir.
So in my half adder, I have given the name half adder here. So I'm copying that. Control C. So Control V. U1. Okay. So U1 is having the inputs carry and S1 and sum and S3. Okay. So carry in and S1. Okay. And sum is what? Sum is S here, and S3 is there, right? So this is the S3. Again, half adder. U2. So it is having the inputs P and Q. And having the outputs S1 and S2. S2. Okay. Then there is a OR gate. The instance 3 I am saying. So OR gate will be having the input S2 and S3 and output is C out. S2 and S3. Yes. So first output, then S2 and S3. And module. Good. Adder. Okay. Have you checked that, Mohammed? Have you defined in the same fashion for half adder first two inputs sum and carry? Otherwise, your position will be different, I think.
No, sir. Same position, sir. First are
Yeah.
inputs followed by outputs.
But for first sum, na means sum and carry.
Yes sir, yes sir. First
हाँ
sum
ठीक
then
है
carry.
तो इट्स ओके. Yes. Now again create one file for the test bench of this. So I'm creating one file. So I will say that as a module EB half adder, any full adder, test bench for full adder. And then what are the inputs here? P, Q, C in. Okay. H, P, Q. So here I will use, instead of X, Y, Z is used here. ठीक है. I can use P, Q in only. P, Q, C in. But last time this model has given the error over that. ठीक है, let us see. Wire. I have created the full adder flow here. Different name I have mentioned. ठीक है, so wire are the outputs, so that is S and C out. After doing this, I need to instantiate this, so full adder. Who I will give. Then initial begin. So first I will give the value of PQCN 0, 0. In will be 0. 1 I will give. Okay. So Control C #10 Control V. So now I will put 1 here. #10. Just give the space in between, okay, properly. Control V. So all 1 combinations. Okay. And after that I will end this. Then end module. Okay. Control S. So full adder TB, no? TB underscore full adder dot V. Okay. So you write down. Just try to compile it. कहाँ पे भाई? ये अलग में है. यहाँ पे कौन तो है?
Sir, it is giving error again, sir.
where it is giving error?
Sir, same error that we earlier rectified, sir. Port S not declare input output. Port C out not declare input output.
For the elaboration?
No, sir. While compiling, sir. Compiling the main file.
Okay. Okay. So one thing we will do, we have rectified that using a different name, right?
Different name, sir. Yes, sir. Yes, sir.
Because what happen if you do this in Xilinx, it will give you correct, but this compiler, Cadence compiler is not giving that correct. Okay. So you just change it name. So I am also changing the name. So,
Okay, sir.
So what name we should do now? ABC is used by me. XY is used. PQCN is used. And so I will use ABC kind of thing. A, B. C is not used, right? So ABC, E, and F.
Sir, not in the test bench, sir. In the main file, sir. Fullheader.v.
In the main file, how it is giving the error? I thought in test bench.
No, sir. In the main file.
In main file, it should not give the error because what variables you have used for half adder? I have used XYZ, XY, sum and carry.
Yes, sir. I have also used different variables, sir.
A, B, sum, carry. So this should not be the case then. So I just need to check your what. Okay. In your full adder dot. Okay, okay. I will just check it.
Okay, sir.
Okay. So what kind? Let me operate your PC. So
Yes, sir. I got the error, sir. Sir, output. That's the output definition for SNC out.
what? I'm operating your PC. Where you got me?
Yes, sir. Yes, sir. Yes, sir. You only operate.
हाँ नहीं means
Sir, after input PQ scene, I haven't declared outputs S and C out.
okay. हाँ you have you haven't mentioned those.
Yes, sir. Yes, sir.
I thought you got error in test bench. That's why I told you to change the variable name. Okay. मैंने देखा ही नहीं था मैं मेरे पीछे ऑपरेट कर रहा था ना.
हाँ ना सर.
हाँ you do this.
Okay. आ गया क्या करेक्ट?
हाँ सर, आ गया, करेक्ट है सर।
Good. So I will show you another design into this. So just exit this. So this is a 4-bit ripple carry adder. Okay. So you may have studied this in digital design. So in this 4-bit ripple carry adder, uh, there are 4 full adders, right? Okay. And those full adders are connected with each other. So it is having 4-bit input, means like 3 to 0. Okay, A and B, and this is the C in. This is the input carry, and this is the output carry, right? So if you talk about this module, so in this module, these are the inputs, right? uh, A and AB input and C in is input, and the C out and S are the outputs. So all these are vector inputs and vector output. So AB is from 3 to 0. So if you mention this like input 3 to 0, okay. Similarly, you can mention like output uh, 3 to 0. That will be S, right? So this will be like a S of 0, this will be S of 1, S of 2, and S of 3. Similarly, this is B of 0, B of 1, sorry, control Z. So this will be A of 0, okay, B of 1. So similarly, other signals are there. Now here you can see these are the external pins. So external input output is there, but these are the internal wires. Okay, this is first, second, third. So 3 internal wires will be required. So you can also take like a wire 2 as to 0. Okay. So internal wire, if I say that is W, yes, you can mention W, no issue. So this will be uh, W0, you say, this will be W1, you say, this will be W2, you say. So in this way, you can implement this 4-bit ripple carry adder like that way, using that full adder. Okay. Or should we move to the next topic? What do you think? Yeah, we want to.
नेक्स्ट टॉपिक करते हैं सर।
हाँ हाँ, ठीक ठीक
सर
है,
इसमें
ठीक।
4 इंस्टेंस बनाना पड़ेगा ना?
हाँ हाँ, 4 इंस्टेंस बनेंगे इसमें। ओके, ठीक है। सो
सर इसका कोड होगा तो बता दो ना एक बार सर।
नहीं नहीं, मुझे भी करना ही पड़ेगा, वो झाइलिंग्स में है। ठीक है,
अच्छा,
झाइलिंग्स का बता दो, देखता हूँ पहले।
इसका अगर हुआ तो अच्छा है।
भी हाँ, ये है यहाँ पे।
हाँ,
तो इसको मैक्सिमाइज करना पड़ेगा, ठीक है। Now is this visible? This
यस सर, यस सर, विजिबल।
so this is a code for ripple carry adder. So here you can see 4 instances we have taken and just made the connections. So for internal wires, I have taken 3-bit internal signal. Okay, and other input outputs, you can see that AB inputs are having 4 bits, C in is single bit, and output is also 4-bit, and one output C out is a single bit, and we have made the connection like that way. So in such a way, you can implement the ripple carry adder. Now, have you implemented this using a case statement? Okay. So you have implemented that. So I'll just move again, move ahead. तो डी फ्लिप फ्लॉप ले लेगा. So now we will see the D flip-flop arrangement, okay? So how the sequential circuit is implemented in this particular flow. Okay, so now create a new file, and here you just put this code. So here I save this. So here you can see. So I have defined the model D flip-flop. As you know, D flip-flop is having clock reset. So reset is not there. So if reset is also there, but in this code, I have used input D, clock, and output Q. Okay. So here you can see two inputs are there, D and clock, and output is Q here. Okay. Now, when you put this as an input and output, default data type for that is a wire. Okay. So you can't use a wire element on the left hand side. In always block. Okay. So that should not be present at the left hand side in the always block. So for that purpose, I'm using one resistor, that is resistor Q underscore A, and that resistor I'm mentioning here, Q underscore A, using in this always block. Okay. Now, this always block is sensitive to the positive edge of the clock. If you put here neg edge, so that will be sensitive to the negative edge of the clock. So similarly, pause edge and neg edge is for the rising edge and falling edge. So in the begin and end, now here you can see in the previous codes, we have directly used this kind of operator. Okay. But here we are using this operator. So this operator is called as a non-blocking operator. What is mean by that? So if I mention here, if I put like this Q underscore B is equal to Q underscore A. Okay. So if I mention like this, so what will happen? First, the right hand side will be get evaluated, means value of D will be get evaluated, and value of Q underscore A will be get evaluated. Okay. And at the positive edge of the clock, those value will be get assigned to the Q underscore A and Q underscore B. But okay, so this is called as a non-blocking statement. And if we talk about a blocking statement, in blocking statement, what happened? So this is the blocking statement. So first D will be at the positive edge of the clock. First D will be assigned to the Q underscore A. After that, this Q underscore A will be assigned to the Q underscore B. Means value of D only be putted into the Q underscore B. Okay. But in case of non-blocking statement, what will happen? Value will be get swapped. D value will be get swapped with Q underscore A. Yeah, sorry. It's just like D value will be D and Q underscore value will be evaluated before the age of the clock, and at the age of the clock, those value will be get assigned. So there will not be any overlap kind of thing. Okay. So that is the difference between blocking and non-blocking statement. So I'm using a non-blocking statement here. So for every sequential circuit, you need to use an operator like this only. Okay, non-blocking operator. So I'm saving this. Now for this, I need to create a test bench. Okay, so for this flip-flop, you can write a code for this flip-flop. So we can go for the test bench.
Okay, sir.
Okay. So now
Okay.
we will write a test bench. So I have already with me the test bench is there. Okay. So here you can see in the test bench I'm using D and clock as a reg and Q as a wire, and then I have instantiated that D flip-flop. So D flip-flop is my module, so I have instantiated D flip-flop. I have given the instance name U1, and here you can see for the clock generation, now we need to generate a clock, right? So for that purpose, I have used this. First, I have initialized the value of uh, clock is equal to 0. Then after that, I have used forever. Forever means no condition is required to repeat this statement. Okay, so it will get repeated until you don't stop the simulation. Okay, so it will generate clocks. It will toggle the clock signal after 10 time units. So initially that clock is equal to 0. So what will happen? Value will get toggled and it will be get assigned to the clock again after 10 time units. If one time unit is equal to 1 nanoseconds, so after 10 nanoseconds, this clock will get toggled. So this is for the clock generation. Okay, so these 4 lines are for the clock generation, and after that we have given the inputs. Okay, so here no need to give this non-blocking statements. You can use a blocking statement. Okay, so like this way you can do the test bench for the D flip-flop. So you just write this test bench.
Okay, sir. Sir, in Verilog, the initial block is similar to process block, right, sir? As we compare it to VHDL.
No. Always block is like a process block, okay? Because in process block also we mention sensitivity listener. So whenever signal will get changed, following code will be get executed. I have explained you the always block in case statement,
Yes,
right?
sir. Yes. Right, sir.
Uh,
So we can say that initially similar to that stimulus process. We right now, sir?
yes. Stimulus one time execution.
Yes, sir. Yes, sir.
Yes.
Okay.
Hmm. ओके, वो नॉन ब्लॉकिंग स्टेटमेंट मत यूज करो टेस्ट बेंच में, ब्लॉकिंग यूज करो। Control S and then do the launching. एरर आ रहा है क्या?
हाँ सर, एरर
क्या एरर है?
सेमीकोलन में।
जो तुमने कंटिन्यूअस असाइनमेंट यूज किया ना, वो कॉन्करेंट स्टेटमेंट है, वो नॉन ब्लॉकिंग नहीं होना चाहिए। जो प्रोसेस के अंदर है, जो ऑलवेज के अंदर है, वही सिर्फ नॉन ब्लॉकिंग होना चाहिए। जो बाहर वाला है ना, वो सब कॉन्करेंट होता है। हाँ, डीप को ओपन कर दो, वो जो असाइन किया है ना, वो कॉन्करेंट है, उसको कभी वैसे नहीं करते। ये वाला है, ये जो नीचे वाला है ना, ये कॉन्करेंट है। ओके, ये बाहर वाला, ये ऑलरेडी अपन ने असाइन यूज किया है उसको, तो वो पैरेलली एग्जीक्यूट होगा। ओके, अभी देख करके।
हाँ
हो गया। टेस्ट बेंच क्या है? अभी उसको पॉज कर लो, क्योंकि हमने वो टेस्ट बेंच में उसको स्टॉप करने को लिए नहीं बोला, तो वो चलता ही रहेगा।
हाँ सर,
अगर
फॉरएवर
मैं
बोला है ना अपन ने।
कुछ टाइम पीरियड दे दूं उसको, सो जैसे 150 दे रहा हूँ, उसके बाद ये डॉलर स्टॉप कर देता हूँ। तो अभी ये टेस्ट बेंच में ये डाल के देखो, जो जो पहले दिया हुआ है वो पा, टेस्ट बेंच में $50। ये जो है वो सिस्टम का टास्क होता है, मतलब देर इज अ फंक्शन एंड देर इज अ टास्क इन वेरीलॉग। ओके, सो ये बराबर एंड के बाद लिख देना वो, क्योंकि हमें इनिशियल के अंदर नहीं स्टॉप करने का, नहीं तो वो इनिशियल के फर्स्ट टाइम में ही स्टॉप हो जाएगा। एक बार देख लेता हूँ मैं उसको करके। नहीं, ओके, वो अंदर ही ले लो उसको, क्योंकि क्या है वो बाहर पूरा कॉन्करेंट आ रहा है। ठीक है, अंदर ले लो। ओके अब आ गया, स्टॉप हो जाएगा अभी। अभी देखो यहाँ पे 100 नैनो सेकंड को हमने इनपुट को 1 कर दिया, बट उस टाइम निगेटिव एज ऑफ द क्लॉक था। ओके, सो इन द नेक्स्ट पॉजिटिव एज ऑफ द क्लॉक दैट आउटपुट विल गेट शिफ्टेड टू द इनपुट, राइट?
राइट सर, राइट।
सॉरी, दैट इनपुट गेट शिफ्टेड टू द आउटपुट। ओके, जो डी में है वो क्यू को गया, राइट?
हाँ सर, क्यू फॉलोज
तो
डी।
निगेटिव एज पे हमने 1 कर दिया ना उसको, पहले 0 था तो 0 दे रहा है, उसके बाद वो 1 आ
हाँ
गया।
सर, बराबर।
ओके, अभी
और सर ये 0 to 10 में अनडिफाइंड स्टेट दे रहे हैं ना?
वो जो फर्स्ट है ना, अरे ये निकल गया, यहाँ पे जा रहा है, कुछ तो बोल रहा है क्या वो? एक डिस्कनेक्ट हो गया था। कुछ नहीं, ठीक है। हाँ, सो so can you try for 4-bit register, like serial in serial out 4-bit register, Mohammed, or should we
हाँ सर,
move?
ट्राई करता हूँ।
हाँ, सीरियल इन सीरियल आउट को ट्राई कर लो। क्या उसमें क्या करना पड़ेगा? अभी ये जो सिक्वेंशियल स्टेटमेंट किए ना हमने, मतलब ऐसा, इसको क्लोज कर लेता हूँ मैं, और ये ब्लॉक है ना, तो इसमें क्या करना पड़ेगा? ये जो नॉन ब्लॉकिंग स्टेटमेंट है, सो जैसे कि मैं डायग्राम निकाल लेता हूँ, उसको समझ में आएगा फिर। ये ऐसा शिफ्ट रजिस्टर है अपना, तो इसको मैंने Q0 सॉरी Q0, Q1, Q2 और Q3 बोला है। ओके, तो ये मेरा D0 हो गया, ये फ्लिप फ्लॉप 0 है, फ्लिप फ्लॉप 1, फ्लिप फ्लॉप 2 और फ्लिप फ्लॉप 3, और ये सारे एक ही क्लॉक पे ऑपरेट हो रहे हैं, मतलब ऑलवेज पॉज एज ऑफ द क्लॉक, राइट? सो तो अभी क्या होगा? So like this way you can assign, like when q of 0 at the pause edge of the clock, d will be get assigned। okay, अभी इसका जो है वो d1 है, राइट? ये d0 है, ये d2 है, और ये d3 वाला है, राइट? तो ऐसा कर सकता है, तो पहले d0 q of 0 को असाइन हो गया, फिर इसमें q of 0 will be get assigned to, किसको बोल सकते हैं अभी, ये D1 के लिए, राइट? और ऐसे ऐसे कर सकता है तू।
लेफ्ट शिफ्टिंग सर।
हाँ हाँ हाँ, ऐसे। सीरियल इन सीरियल आउट।
सीरियल आउट।
नहीं तो उसको ऐसे भी करने की जरूरत नहीं, पर D1 असाइन नहीं होगा उसको, क्योंकि उसका स्ट्रक्चरल करना पड़ेगा फिर, नहीं तो।
हाँ वो स्ट्रक्चर करना पड़ेगा, फिर 4 फ्लिप फ्लॉप लेना पड़ेगा।
नहीं नहीं, ये ब्लॉकिंग स्टेटमेंट से हो जाएगा, बट उसको क्या है कि पहले ये सब असाइन होगा। तू ऐसे कर ले, मतलब D ऑफ 0 विल बी असाइन टू Q ऑफ 0, Q ऑफ 0 विल बी असाइन टू D1 सिमिलरली। तो कैसा होगा कि पहले जो राइट हैंड साइड है वो इवैल्यूएट होगा,
हाँ सर।
राइट, और पॉजिटिव
राइट
एज
सर।
ऑफ द क्लॉक सब स्वैप हो जाएंगे, इसको वो उसको, राइट। तो ऐसे कर सकता है, एक बार करके देखो, मैं भी करता हूँ तेरे से, ठीक है।
हाँ सर सर।
Okay. Now we can talk about some operators. Okay. So important operators which are used in Verilog. So in most of the languages, in C language, you may have seen the arithmetic operator like this only, but there are some few different operators which are present in the Verilog. Okay. Uh, so so as you know, the arithmetic operators like addition, subtraction, multiplication, division, modulus, exponent, all are available in this Verilog also. One more thing is that, for example, if A is like a 2bx, okay, and for example, B is 2b01, okay, and if I do the addition of these two, right, so now A is having the unknown value. So result of these two, if I say that is, if result of these two, if I say that is C, okay, so that result will be having, that result will be, okay, sorry. You should tell me. मला आवाजच येत नाही, कोण बोललं का?
मलाही दिसत नव्हतं आणि ती मुलं कशी ऐकतात तेच कळून.
Are you listening?
Yes, sir.
Yes, sir.
So I will just explain you some important operators here. So अरे बोले भी नहीं लड़के मैंने खाली चालू कर दिया एक्सप्लेन करने को, बोले भी नहीं. Okay. So here if you see, if in Verilog also there are different operators, just like arithmetic operator which we use in other languages. But one difference here that, for example, if A is having value 2bx, okay, unknown value, B is having some value 2b01, okay, and if I do the addition of these two and if I assign that to the C, so C will contain, entire expression will be having the x value only, because this operand consists of x value, okay. So this is about arithmetic operators. So all of you know those operators, okay. So I will just tell you about some exceptions here. So all the things are that only. And if you talk about a logical operator, so this is a logical NOT, logical and logical OR. Okay, so in this way you can perform logical NOT, logical and logical OR operation. So this is all about, even if here also, if any one of the symbol is having like X value, okay, so result will be X only, X or Z. Then there are relational operators. All of you know this operator, greater than, less than, so no need to explain. Now, if you talk about the equality operators, so one difference is here. As you know, this operator is equality operator and this is a inequality. But in Verilog, there is a case equality and case inequality. So what is mean by this? So as we know, in Verilog, there are 4 logic levels: 0, 1, unknown value, and high impedance. So these 4 logic levels are present in Verilog. Now, if you talk about case equality and case inequality, I will just show you the example here. So here you can see B number and B variable and C variable. Okay, so B is a 4-bit number and it consists of unknown value X. Okay, 1 0 X 0 binary number. Similarly, C is a binary number, 4-bit binary number, consists of value 1 0 X 0. Okay, so these two things are there. If you use a normal equality operator, so here I am using a normal equality operator. So what normal equality operator will give the result? It will result X. Okay. As you know, if any one of the operand consists of X, entire result will be X. So it is returning X, right? But instead of normal equality operator, if I use a case equality operator, so what result it will give? It will give the result 1, because even if there is an unknown value, both consist of unknown value at the same place. Okay, so these numbers are same by looking that. So if you use a case equality, it will give the result 1. So this is one exception present in the Verilog, because it is having 4 logic levels. Okay, so this is about case equality and case inequality. Okay, then there is a bitwise negation. For example, if A is 4-bit number like a 0010, B is 4-bit number like a 0100. Okay, and if I use a bitwise OR on that, so what will happen? A bitwise OR with B, so bitwise OR will be done here. Okay, 0 OR with 0, 1 1 0. So this will be the result. So this will be the result. Okay, so bitwise operators are there. So this is a bitwise OR, bitwise XOR. Similarly, bitwise XNOR operations are there. Okay, so these are all the bitwise operators. And one of the important or exceptional operator in Verilog is reduction operator. So what is mean by reduction operator? For example, if A is having value 4-bit value, B 0010. Okay, and if I apply the reduction AND on A, so what it will do? It will do the ANDing of this. So it will AND 0 with 1, so the result will be 0. Then 0 will be ANDed with this, then that result will be 0. Again 0 will be ANDed with this 0. So result of this operation, if I assign C is equal to reduction of A, so C will be having the value 0. Similarly, if you apply OR on that, reduction OR, if C will be reduction OR, so it will give you single value, 1-bit result it will give. Okay, so this is a reduction operator. So if I do reduction OR on A, so now my A is what? 4 tick B 0010. So 0 will be OR with 1, so result is 1. 1 will be OR with 0, so result will be 1. And again 1 will be OR with 0, so result of this will be 1. Okay, so it will apply that OR operation on this entire bit stream. Okay, so that operator is called as a reduction operator in Verilog. Okay, so this is important. And then there are arithmetic shifts and arithmetic right shift and left shift operations are there. Okay, so concatenation operator we have seen. Now the replication operator. This is one of the important operator here you can see. So syntax for the replication operator is like how many times you want to repeat that particular value, okay, particular variable value. So replicate underscore times, then operand is there. So curly brackets are used. Now here, if you see the example here, if A is equal to 2-bit number, which is binary number 0, 1, and B is a 1-bit binary number 1, okay, and I'm using a replication operator on this A, okay. So A will be 3 times of, so A will be, A operand value will be repeated 3 times. So here you can see A value is 0, 1. So it is repeated 3 times, 0, 1, 0, 1, and 0, 1. Okay. So like this way you can use a replication operator. Okay. So this is about a replication operator. You can use like that. And there is a conditional operator, the last operator I am talking about. As we have seen, this question mark like symbol is also used for the high impedance, but if that used with some like in concurrent statement, in the assign statement, so that will be like a conditional operator only. So you have seen this ternary operator in other languages also, like in C you have seen that. So syntax for that is the condition, okay, if condition get satisfied, so this will be the expression. If condition is not get satisfied, this will be the expression. If you see the example here, if the select is 1 here, y1 will be assigned with A. If select is 0 here, y1 will be assigned with B. Similarly, here you can see, here they have mentioned the condition. When select is equal to 2, input 1 will be assigned to the y2. Or if this condition become false, ion 0 will be assigned to the y2. Okay. So like this way, there is a thing. Now, can you tell me what this expression implement? Which kind of logic this expression will implement? Can you tell me? This last one using a ternary operator. So we can conclude here after doing this. So what do you think? So which block that assignment, that statement will get produced? Which hardware? Any idea?
No, sir.
थोड़ा सा लॉजिक लगा के देखो ना. अभी यहाँ पे देखो अब when select 1 is equal to 1, out of these two equation, which equation will be get satisfied? Which expression will be assigned to y3, you think? So out of this, if select 1 is equal to 1, so this, right? So this will be the expression, right? And if select 2 is equal to 1, then A will be assigned to the y3. So y3 will be A in this condition. Okay. And if select 2 is equal to 0, B will be get assigned, right? So when select 1 is equal to 1, select 2 is equal to 0, B will be assigned. And if select 1 is equal to 0, then this equation will be get true, right? So here, if select 2 will be get 1, y will be C. I will just if select 1 is equal to 0, so this equation will be get true. And if select 2 is equal to 1, so output will be C. Or if select 2 is equal to 0, output will be D. So for this, when select 1 is 0, select 2 is 0, output will be D. And when select 1 is 0, select 2 is 1, output will be C. So which kind of block is this?
Sir, multiplexer.
That only. So how much that means 4:1 mux, right?
Yes, sir. 4:1.
So within one line also you can implement that mux using this ternary operator. Okay, so as I have covered the basic of this particular language, okay, so there are different construct like for loops, other block statements. So this, if you want to refer this thing more, there is a book called Samir Palnitkar, Verilog HDL by Samir Palnitkar. That book is also good because in this short time it will not get completed. So it's just like I will show you. So Verilog HDL by Samir Palnitkar. Okay, Verilog is very simple language by Samir Palnitkar. इसका PDF मिल जाएगा, नहीं तो मैं ग्रुप पे डाल दूंगा. So this is also a very good book for this. So whatever the PPTs are here, I have just summarized that from that only, but in the concise manner. Okay. So I think here we can conclude today's session. Do you have any doubt? Sorry. Do you have any doubt?
No, sir. No, sir.
Okay. ठीक है. So we can conclude this session here. Thank you for attending. And
Okay, sir.
I can conclude this. You can leave. Yes.
Sir,
हाँ बोलना.
सर वो प्रैक्टिकल्स तो अभी सेकंड सेम में होंगे ना?
हाँ वैसे ही बोला है, मतलब मे बी इन द सेकंड सेम ओनली.
ओके सर.
हाँ
तो
हाँ
सर तब हार्डवेयर पे भी अपने को प्रैक्टिस करना पड़ेगा क्या सर, या फिर वाइवा में हो जाएगा?
क्या मालूम अभी क्या करते हैं, अभी कुछ बोला नहीं है अभी. कुछ नहीं, अभी हार्डवेयर में तो कुछ इजी ही है, मतलब कुछ नहीं, थोड़े से एक दो स्टेप करने पड़ते हैं सिंथेसिस के बाद, प्लेसमेंट एंड राउटिंग वो थोड़ा सा होता है, कुछ नहीं वो इजी होता है. बट
ठीक है
हाँ.
सर. और अभी तक कुछ नोटिस नहीं आया रीओपनिंग का?
नहीं अभी तक तो कुछ नहीं बोला, रीओपनिंग का कुछ नहीं बोला अब तक.
ओके सर. ठीक.
हाँ.
थैंक यू सर.
ओके. हाँ ठीक है चलेगा. थैंक यू.